right, we're talking about some sample problems from section 4.5, various ways to solve equations with logarithms and exponents. And so now we revisit our compound interest formula. You might remember this formula from, I think it's section 4.2. So all we could do in 4.2 is if we knew A or P, we had to know one of those, but we couldn't solve for the exponent. That's what opened up for us in section 4.5. We've learned how to solve for the exponent by using logarithms. So the last problem we did, we were solving for the exponent. This one actually, we're solving for a new place. We're solving for the rate, which is kind of a new perspective on it too. So in this sample problem, it told me that you want $2,500 as a start value to grow to $3,000. You don't know the rate, and it's compounded semi-annually, which means twice a year. So notice for n, I plugged in 2, and then it did give me time, which is 3.5. I was thinking of the last problem we did. We were solving for time. But here we do know time is 3.5 years. So I recommend you always just go ahead and multiply these exponents together. It makes it easier to type in your calculator. So I would just say do that up front. Then try to do anything else you can do to reduce this down, like do what's in the parentheses. If I could, I would do that next, but I cannot because I don't know R. So then I have to start working backwards. So the first thing I can do here is divide out, because that's multiplied. I'm going to divide out by 2,500. And that leaves 1 plus R over 2 raised to the 7th equals, and I can type this in. If it's not one of those terrible decimals, I'll write it down. Otherwise, we'll keep it intact like we do to avoid round off. But that comes out nicely to be 1.2. So now we're to that point where we've before in our homework where we have two bases here. We have these two sides, and sometimes both sides are raised to an exponent. This one only has the one side raised to an exponent. But to solve that, but I can't do it. Actually, I was still trying to solve for the exponent for you, like the other problems. I cannot take it to the 7th power, though, because I don't know what this is. So I'm still having to kind of reel backwards to work this backwards. So what I can do is take it to the 7th root. So the 7th power, 7th root, cancel each other out, releases that 1 plus R over 2. But you know, whatever I do to one side, I will need to do to the other side. So 7th root that side. So how do you take the 7th root of 1.2, you might say? That might be the first time. This may be the first time we've had to do something like that in this class. So some of you have an X root button. Do I even have one? I have it in the math. You can go to like a deeper function. And then here's a simpler calculator. Let's see if it has an X root. Nope, I don't think I do. Some calculators do have an X root button. So if yours does, you'll type in 7, hit your X root button, so that makes it the 7th root, and then type in the 1.2 equals. Some of you can do it that way. In your graphing calculator, it's usually under math. So I'll have to type in my 7 and then go into the math function. And you'll see it's the 5th one down, X root. It is in there, but you have to kind of work for it. So the 7th root of 1.2. So I can do it that way. If none of that works, everyone can do this. Instead of writing it as the 7th root, another way to express that is 1.2 to the 1/7th power. We can always change a radical to an exponent by saying the exponent here is understood to be 1, so this is the root, that's the denominator. When you change it out of radical form, it would be 1.2 to the 1/7, whatever the root is, power. So you could do it this way. Now let's just check that on my calculator, see if it's the same answer. 1.2 raised to the 1 divided by 7th power, and notice it is exactly the same. So either way, I don't want to write that down though, because I'm going to compromise the decimal value, so I'm going to leave it like that. And then to finish solving, I'll bring the 1 across. So whatever 1.1 says, minus 1 R over 2. Sorry about that. Then the last step is I would times that by 2 to clear that divide. I'll multiply. So I'll divide this side by 2. And then R will be all of this typed in. You could just leave this calculation in here and go ahead and say minus 1, do the parenthesis part first, and then times 2. and that's going to be my decimal value for the rate. Now to make it a percent, we need to move this decimal 2 places right. So it's going to be 5.27761 as a percent. Now it should tell you what place to round to. So depending, but it says rounds to maybe 1/10 of a percent. That would be in tenths place. After you move your decimal, 1/10 of a percent, the 2 would be rounded up to a 3. So I would say to the nearest 1/10 of a percent, that would represent 5.3% makes that happen. All right, number 22. The last couple of examples I have here for you takes us back to something old as well. We're wrapping in some old with some new here, and it's finding an inverse function. That was in the first section of chapter 4. So an inverse function, first of all, to find an inverse, it has to be a one-to-one function. So we should look at this and say, do I know what this looks like? If you're using a graphing calculator, you can know what it looks like. But again, I do not encourage the graphing calculator, but if you are using one, feel free to use it here. But I would say, type this in my y equals e to the x minus 6 power. Where's that x? X minus 6. Oops, minus 6 and close. Okay, graph that. Okay, and you'll see this exponential function. The graphing calculator has a hard time differentiating where the asymptotes are, but it looks like it's running into the x-axis, and it's not. It's hovering over it. So I would draw it more like this. It looks like this, kind of hovering over that, right? Now it is an exponential function. We saw that earlier in the chapter. E is almost 2, so for example, it's very close to that equation. Y equals 2 to the x minus 6. Remember, E is about 2.718. It's an exponential value, not exactly 2.718, but it's around 2, 2.5, 3. It's going to look similar to 2 to the x minus 6. Well, we learned that, say, 2 to the x in regular form go to 0.01. That's an exponential function in standard form. So if we put this minus x on it, which shifted over, remember that's grouped with the x, so that's a left-right shift, and it's opposite of what you see. So it's going to move this over 1, 2, 3, 4, 5, 6 place. So it gets shifted over 6 places, and thus that's why that on your graphing calculator view. But anyway, if we could figure out the domain and range of this, it would be handy for when we find the inverse. It's just going to flip domain and range, switch places. Oh, also back to the reason I graphed it is to determine if it's one-to-one. And it is. If we draw a vertical line, nothing repeats vertically, and we can draw a horizontal line. This thing looks like it almost does, but it's ever closer and closer to that x-axis, not really repeating itself horizontally, but inching closer to the x-axis as an asymptote. So there is no repeat, so yes, it is one-to-one, meaning yes, it should have an inverse function that we can find. You might remember inverse functions in the x and the y switch places in every way. Physically on our, and I'm going to get rid of this because we're going to use our actual value e exactly for our problem. And we're going to switch, this is the y and this is the x, we're going to switch places. Instead of having y equals e to the x minus 6, the inverse will be x equals e to the y minus 6. And then we'll rearrange that and solve that for y. But first of all, let me back up and find the domain and range of the original function, because while I've got this nice graph here, we can see the domain is going left and right without bounds, so that's negative infinity, positive infinity. And the range, though, is stopping over 0. It's not touching 0. Remember, that's an asymptote, so it's 0 with a parenthesis and then on up to positive infinity. So whenever the question asks you to find the domain and range of the inverse, we'll just flip those, right? Domain will be range and range will be domain. All right, so let's find that inverse function. So we had to wait until we learned how to solve for exponents in this section before we could do this. But to get this y minus 6 out of the exponent position, we're going to have to take the logarithm to do so. So we'll take the log of each side. Now normally log or ln, it doesn't matter, but when e is involved, ln plays not with e. It simplifies easier. I recommend ln log of each side. That makes the left side ln of x On the right side, because it's a log, the exponent is now down in front of that as a multiplier. Y minus 6 times ln e. So ln of e is just simply 1. You can type that in your calculator and see ln of e is always 1. So now we have ln of x equals y minus 6. Nothing to distribute there. So to finish solving for y, we throw the 6 across. Ln x, that'll make it plus 6 equals y. So, so whenever we finish doing that, we can then graph y. Instead of y, we'll call it f inverse of x equals ln of x plus 6. And so the graph, if you wanted to, you could type that in your calculator and see what it looks like to determine the domain and range. Oh, let me scoot that up for you, sorry. But we have that calculation already found earlier that said the domain of the earlier one was negative infinity to positive infinity, so that'll be the range now of this one. And the domain will be the range of the original, so those two just switch places. Now let's look at our calculator and see how that looks, just to kind of show that if you're doing it that way, if you like to look at the calculator version. Ln of x, let's see, where is that equation? And then ln of x plus 6, and let's graph that. Okay, so it was the regular log graph. Normally that goes through 0, 1. Down here, you know, the log functions 1, 0, sorry, goes through 1, 0 typically, but it scooted that up 6 places. This is considered a vertical shift when it's on the end like that. That's a vertical shift. So it scoots the graph up 6 places. So you see, normally the log function is down here, scooted up, vertically shifted up 6 places. Notice the y-axis is an asymptote. That's why the domain is 0 to infinity. It's not touching 0. In the range, it's up and down. This thing would keep coming down. But again, the display has trouble showing that. But the graph does continue down to negative infinity. So then the range infinity, infinity. All right, let's see if we can get one more in before we close out. Okay, one more example. Another example. Another sheet of paper, guys. It's really the same question. I just want to get another practice of that in with you. Maybe I will, maybe I won't. Okay. All right. So 23 is basically the same question, but just thought we could stand to do that one more time to practice that. All right, 23 says to do the same thing. Find the inverse function for e to the x plus 5 minus 8. So we talked about how that e to the x is an exponential function. Those are one-to-one functions, so we will be able to reverse this and switch the x and the y. That's how we find inverses. Then resolve for the new y, so we can throw the 8 across the line. It makes it x plus 8. Always reduce it as much as you can, simplify as much as you can before doing your log rules. So I would move that 8 across first. Then to get this exponent to come down, that's our big new move in section 4.5 by taking the log of each side. We can do that. So we take the log of this side, the log of that side. So the ln of the side, x plus 8, equals the ln of e with the y plus 5 now brought down. Sorry, I forgot to write that in. So it looks like this. The y plus 5 is in front of that, right? The exponent comes down in front of that as a multiplier. Ln of e is always 1, so we can kind of just forget about that, you know, multiplying by 1. So to solve, we just have to throw the 5 across the line. And there is our inverse function. Y equals, which we'll write it as inverse function, f inverse of x equals. And then we can look at that graph to see domain and range, how that's been shifted. You know, the regular log graph in state form without shifting goes through the 1, 0. And again, because it's in parentheses, that's the x shift. It's grouped with the x. It'll move it back 1, 2, 3, 4, 5, 6, 7, 8 places. and then this will shift it down, which won't really affect things as much, but as far as how it looks, it does. This point is moved back 1, 2, 3, 4, 5, 6, 7, 8, and then move down 5 places, same shape, but just shift into new spot there. So the domain, what would have been at 0, the domain moved back 8 places. So the domain is -8 to infinity now. So it's moved back. The asymptote was at 0, but it shifted back 8 places. That affected the domain. Now the range, the -5, it didn't move down 5 places, but the range is going up and down without bound. So the range is, let me write that down, is all open there, up and down without bound, infinity, infinity. All right, hope that helps. Let me know if you have questions as always.